Our next speaker is Sergio, and he's going to talk about shrink-free scaling. So I'm going to welcome him up now, and we can all begin this session. And I think your slides are there, so that's even better. So just take it away.
Hello, hello, hello. Thanks, Patrick, for the invitation. Today's talk is about shrinking chain scaling. The name of the talk was, if the blockchain is edited while preserving consensus, that it still make a sound. And the idea behind shrinking chain scaling is that we don't need all nodes to have the same blockchain information. We just need to have the same meaning to be in consensus. But we can actually go back in time and correct and edit the blockchain or compress the blockchain and still be fully in consensus. For those who do not know me, I know many people, but I'm Sergio. I've been in this space since 2011, I think, working on the security of the Bitcoin node. And now I'm a chief scientist on RSK. And just a few words about RSK, which is what motivates this talk. RSK is the first working and active sidechain to Bitcoin, but it uses the Ethereum model of account. It implements a EVM compatible, and it has this Web3 interface. So all applications that run on Ethereum, you can actually run them on RSK. Oh, this is a bit heavy. So while you are all thinking about how to scale, second layer solutions for millions or billions of users, I have to think what will happen with the blockchain, how the blockchain can support the number of on-chain settlements and top-ups of those number of channels. So that's really a problem that you also have to solve. So all these scaling solutions have some meaning in the decentralized network. So in centralized network, none of these has any value. Probably the solutions are completely different, are based on scaling the hardware. So we want to scale and find scaling solutions for a decentralized network. So decentralization has many meanings, but we know some measures of decentralization that can help us have a more decentralized network and scale it. Basically, we want to have the highest number of providers, developers, independent full nodes, wallets, etc. We want this network graph of full nodes to be as highly as connective as possible to prevent splits. And we want that the net cost of running a full node is as low as possible, because we want individuals, not only corporations, to be able to run full nodes. So that's what this talk is about. So what a full node does, it basically validates the blockchain. It broadcasts new blocks and new transactions, and it serves all this information to new nodes that want to bootstrap a new node. But it also provides some collateral services, like hiding information of the whole network, protecting the miner from denial of service attacks, giving filter information to lightweight nodes. But essentially, these three first services are what characterize a full node. Basically, a full node is a node that validates every single transaction. So at RSK, we are thinking that we want our network, or the ecosystem, to reach 1 billion of users. And for instance, we want in the following years to reach, let's say 1 billion, but say 140 million users. So we are sure that these users will not be doing on-chain payments. They will be doing mostly off-chain payments. But every now and then, they will need to go to their channels, top up them, or take funds from their channels, receive their salaries, and put them in channels, whatever. So essentially, this is a kind of a future scenario for the next years. And we need 200 transactions per second, 23 kilobytes per second of bandwidth, and at least 700 gigabytes of disk per year. And approximately in the cloud, that costs about $37 a month. So I'm not saying that you should put your node in the cloud. That's not very secure, but this is just for measuring the difference of node cost. So how many individuals can afford this in the third world, if you want to reach a billion unbanked users? So what are the current solutions? What can we do right now? Well, Satoshi thought about this solution of having SPV nodes. So if the network grows and start processing more transactions, we will have very few full nodes that actually verify everything, and a lot of very small nodes that will be SPV nodes. And this can work. There can be a certain number of SPV nodes, but essentially this is a centralization risk. Another solution that we explore at RSK, and I presented this in the last DevCon, is by incentivizing full nodes. So we created a method called proof of unique blockchain storage, where a smart contract directly pays full nodes from a smart contract for having a single copy of the blockchain. So this is one way that we can incentivize more full nodes. But again, there's other problems, because a full node does not only store the blockchain, it also performs many more services. So there's new ideas now about having proofs that a certain block is valid, so that nodes can validate the proofs instead of validating the full nodes. There is a project called Coda Protocol, which aims to change the task a miner does, that it should not only create blocks, but it should compress blocks by creating assassin proof, cryptographic proofs, that these blocks actually perform the actions required. Well, in this initial setup, this is very promising, but to create this proof, these full nodes require probably 100 megabytes of RAM, and maybe it takes 10 minutes to create such proofs, so it does not work well. It has some very important centralization risk, and also it does not work with a cryptocurrency that has 10 seconds block interval. But even in this setup, nodes have to propagate all transactions through the network. So we can change this and say, okay, let's directly send the transactions to the miners and forget about using the network to send transactions. But then we have worse, more centralized full nodes. So also there are some other solutions regarding with sharding or sidechain, as RSK does, but this is more about connecting blockchains than solving the problem in a certain blockchain. So what if, instead of compressing the information and then propagating that to the network, what if we could just do this and shrink the information post facto, after this information has already been propagated to all the blocks? So we basically create three types of nodes. That tip sync nodes are not nodes that are in real time syncing all the information, validating every transaction. But then we have delay nodes. They still process the whole blockchain. They still have this assurance that every transaction is correct. But since they are delayed, they receive only the compressed blocks, not the full blocks. And we could have a third kind of block that basically is incentivized to create these proofs. So we can create an economic market where anyone can compress the blockchain and send these proofs to the blockchain. Or if we want to make this mandatory, we can just let the miners compress the blockchain. So this is how it works. We have node A and node B. There are tips synchronized nodes that receive the blocks around 100, but they are sending the delay nodes only blocks 1, 2, and 3, which are compressed, are smaller, but are 100 blocks behind. Well, there is a very interesting thing we can do with this setup, is we can create mixed nodes that are SPV synced, so they are synced to the tip of the blockchain with an SPV node, but for full node verification, they are 100 or 1,000 blocks behind. So when these nodes detect that there is a payment using the SPV part of the node, they can dynamically switch to tip sync node and start processing all the information from the last day or so. So basically, they have all the benefits of having much less resources involved, but sometime when they receive payments, let's say once a week, they can switch to full nodes and have fully assurance that the payment they are receiving is correct. So what could we do in the future? I mean, what new solutions will bring this framework? Well, we could have a certain block that has a proof that a whole branch of the blockchain can be compressed into a single, piece of data, which will specify the initial state of the block, the end state, and all the transaction hashes of the Merkle or trie routes so that everyone can map their transactions to these routes. This is something in the future could occur. We will see. We can do something smaller, shorter. Let's say we compress just a block, and we provide just that proof. We can still go down one level and say, OK, we will only compress some transactions. We'll pick some transactions from different blocks, and we will compress them and just write a proof. Or there is something we could do right now that can save a lot of blockchain space is do signature aggregation post facto, after the block has been mined. And there's a lot of benefits of doing this afterwards than doing before the block is mined. So what do we need for this new kind of synchronization, new paradigm to work? We need a different block synchronization algorithm. We need a different tip delay block synchronization, protocol, sorry. We need to define which function we will use for compressing the block. And we need some economic incentives for these new types of compression generation nodes to do their job, or we just make this mandatory and miners have to do this every now and then. Regarding the block synchronization, the idea is very simple. We have some block that we are analyzing to be shrunk, to be compressed. In this case, we are taking away the witness part of a transaction, the signature part of the transaction, and there is a look-ahead window where we are waiting or we expect to receive a proof that this information can go away, okay? So during that window, a proof can appear, and if it does appear, we just mark the information to be deleted. But the information is not deleted right away. There is a new segment of D blocks, and after that amount of blocks pass, then we can actually go to disk and delete information. Okay? This is to allow the blockchain to be reversed and go ahead with the different branch very efficiently. So how do we evaluate if what we are doing really saves money? Because this is about saving money, not saving space. Because if we need to do a lot of this access just to compress information, or we are just compressing very small parts of the information, then we may be spending more money using the CPU than what we save from disk. Okay, so there are two ways we can measure it. One is measuring the cost in a node in Azure or AWS, or we can analyze what would be the gas cost of doing all these operations, assuming that the gas costs represent what the underlying hardware costs are. So this is basically a detail of how much it costs to run an RSK or probably an Ethereum node in an Azure instance. So most of the cost is in the CPU, but we have costs in bandwidth, storage, and SSD storage also. So as I say, why can't we just, in the case of you are aggregating signatures, why can't we do this before? Because aggregating signatures before they go into the block have several problems. It requires a multi-party protocol for coordinating all this. This delays payment, but more importantly, if there are 1,000 or more than tens of thousands of users trying to create transactions, then this protocol will be susceptible of denial of service attacks because there is nothing at stake. You have not paid anything to be part of this protocol. While if you do this post facto, you have paid in advance by putting your transaction with all the data in the blockchain. You have prepaid for the data and from the space that it will be reimbursed to you later. So there are problems with this, and if you want to solve them, you need some kind of reputation, identity, and then you have problem with privacy because everyone will relate your identity with your IP, and then, okay, we have a lot more problems to think of. So this is the first example of how could we use this framework. And this was published, I think, by RSK a year ago. It's basically do signature chaining. So we have a first transaction T0, and we sign it. We sign the hash, but we sign the hash of something that we dynamically compute, which is H0, which obviously is a hash of the information in T0. But later, transaction T1 comes, and what we actually sign is not T1, but we sign a concatenation of H0 and T1. So at this point, we could just remove the information, all the signature from T0, because we don't need that anymore. The second signature is signing both of them. This is very simple. In Ethereum and in RSK, what you need to add is a very short pointer, to put back the information about the source account, because the source account in these networks is extracted by public key recovery from the signature. So at the end, when the third transaction comes, it just has one signature. So you only need one signature per account, probably forever or for a long epoch. And in terms of space, in RSK or in Ethereum, the signature is about 80% or 70% of the space that the transaction consumes. So this is barely the supposed savings of doing this. So both analyses show savings in the blockchain space. In one case, it's 30%. In the other case, it's 45% in the cost. So can we do this with many signatures from different sources, not only from one source? There is a signature scheme called BLS, which is very interesting, that allows this signature aggregation. But so the protocol is again, very simple. When the proof comes, this proof will reference a number of transactions that will be compressed. But the problem is that this signature scheme requires a pairing operation, a cryptographic pairing operation per signature, and that is very costly. So the whole thing, does not bring you any savings. Instead, it has an additional cost. But Dan Bonnet published, I think it was less than a month ago, or about a month ago, a modified version of the BLS signature scheme that has a very interesting property, that you can do something called multi-signatures, which is basically if all the participants sign the same message, then you can actually compress all signatures into a single signature without doing a pairing operation, just a modular exponentiation. So at the end, you can verify this signature only with two pairing operations, which is very cheap. So if you perform 1,000 payments, then you could, you could aggregate all of them and just perform two pairing operations. So this is the final setup we came up with, which is basically a combination of both methods. And you see that account 0 is signing transactions with ACDSA. And why is doing that? Because ACDSA transactions are very, very fast to verify. So we don't need to force nodes to verify BLS signatures. So full nodes are still verifying ACDSA signatures. And every now and then, we have something called an epoch, which has, every 1,000 blocks, there is one special block, which is the key block. So the following transaction from the same source in the key block will not only contain, the standard ACDSA signature of T5 in that case, that is trying to compress the T0 and T1, but it also has a BLS signature of the key block hash. Okay? So by signing the key block hash, you are actually signing everything that happened before that, okay? Because you can basically derive anything from the key block hash. And so it's interesting that the BLS signature does not even need to be verified by anyone. The only that will verify the BLS signature is the miner when the next key block occurs. And when the next key block occurs, the miner will collect all valid BLS signatures and will create this aggregated signature, okay? So at that time, every signature has gone. Full nodes have only validated ACDSA signatures, not a single BLS, one single BLS signature per epoch ever. So all transactions in the blockchain have no signatures at all. Of course, this only works if the same users are periodically doing some transactions. Okay, if a user performs just one transaction, there is no much to save that. Another important thing is that we use future transactions to do the reimbursements, because we are trying to reimburse here is a fraction of the transaction cost. So we cannot just update the balance at a later time, because just the cost to update the balance will cost more than what we are trying to save. So essentially, this setup allows us to reimburse the source account at the same time it's performing another operation, transactions on the blockchain. So we save that cost. So we can see that we can save about 63% of the cost of running a full node. So now we have this new tool that allows us to remove information from the blockchain, and we have this new synchronization protocol that has the look ahead. So what else can we do? Does this tool provide us with more powerful things? Well, in fact, it allows us to create something we also published last year about a new type of information that you can send to the blockchain, which we call ephemeral data or Schrodinger data, which has many useful use cases. This is data that you provide to a smart contract, and it's stored on the blockchain, but if after some time to live, if after some time no smart contract refers to this information by its hash, then the information just disappears from the blockchain. So you know that the blockchain is best used if it is used as a decentralized court. It should be an arbitrator, not anything else. So many of the proof systems we use that we want the blockchain to arbiter are non-deterministic. So the proof is maybe large, but only some people can provide this proof to the blockchain, and then there is a challenge period where anyone can verify the proof, and if the proof is correct, that information is not needed anymore. But if it is incorrect, then the blockchain will execute this proof and make sure that it punishes the right guys. So now we can send this proof to any digital court, to any smart contract, and if no one challenged that proof, then that proof it's eliminated from the blockchain. So we only pay for the data that we propagate through the network, but we don't pay for space in the blockchain forever, and we don't pay for any computation related to that data. And there is an opcode, to retrieve this data. Also, we can do the opposite. I don't know many use cases for this, but there are some interesting use cases, which is default data, which is data that you provide to a blockchain, and if you don't do anything, will stick with the blockchain forever, but you can execute an opcode to remove this information from the blockchain before a certain deadline, okay? So one of the use cases is if you want to create a multi-party protocol where the miners are involved, they have a lot of power, to censor transactions for, closing the channels or whatever. So you can create an on-chain payment channel, an on-chain state channel, where you send every new state to the blockchain. So you have to pay for that, but it's irreversible. And if no one does anything, then the information just sticks forever. But every new state you send, you erase the previous state. So you actually do not use the blockchain much. You just pay for the transaction cost, but not for the space of the state. So as a summary, okay, we are here because decentralization matters, and low full node cost is essential for decentralization. So either we provide some incentives to run full nodes, or we make the cost of running full node as low as possible. And shrinking chain scaling is a different paradigm, a new paradigm to create incentives for using less resources in the blockchain. And one very simple application of this paradigm, this framework, is signature aggregation. And with that, you can compress the blockchain as RSK or Ethereum about 60% with this technique. Okay, thank you. I finished before.
Thank you for the awesome talk. Is there any questions? Yep, one down. I'll go down here first. Here you go.
So one thing that you have to consider with all of these signature aggregation, especially the successive signing of the ECDSA signatures, is that you may be changing functionality. So at present, pretty much all replay protection and signatures is serial. It goes in sequence, but certainly post-account abstraction in Ethereum, that'll be optional. And for state channels specifically, it's not a feature we want. In state channels, we don't assume that we know the order in which our signatures will be going to chain. And so if we were to enforce the signature ordering property here, it would actually prevent us from safely building state channels.
I think I don't try to understand the question. The thing is that if you want to have like non-malleability, you have to segregate the signature. This is one thing. So it should not be part of the transaction ID. That's one thing. The second thing is that doing abstraction, account abstraction, is very bad for many possible compression techniques. So I still think that if Ethereum does account abstraction, it should abstract the signature, the signature abstraction. It should abstract it in a specific field and not just make it part of the data. It interferes with many future ideas that may appear regarding blockchain compression. That's what I understood from your question, sorry.
I mean, the root problem is that when we look at replay protection, so right now replay protection in Ethereum is provided by a sequential nonce.
Yes.
And if you look at a state channel, you have, so for example, in counterfactual, we have many off-chain objects. We have no assumptions about which ones will be going to chain first. So we don't want an ordered property like a nonce that's doing our replay protection. What we want is an unordered nonce, like a one-time use nonce. And then once this nonce has been used, don't use it again, or some property like this. And regardless of how this is implemented, like even if we did segregated signatures in the account abstraction, it would still preclude the type of method that you're using.
I understand now, yes. Okay, so one thing that we've been playing with is having accounts that have many signatures. So you can implement state channels in a way that is compatible with this design. Okay, so basically you create accounts that can be controlled by more than one key, and then you just fashion, the state channel update with the account control. So basically, you just segregate the signatures of the participants of the state channel protocol, okay? But we have not implemented that. But you can use this technique and still be able to update a state channel without worrying about the nonce.
Yeah. Okay. We can take that offline anyway. We can take another question.
Yeah.
Make sure everyone has it. Any more questions? Okay, I don't see. Oh, there's one. Where? Oh, there you go. Yeah.
So, do you have any plans to sorry. So this lets you compress the blockchain, but I don't think it lets you compress the state. Sorry. You can't compress the state.
The state?
Yeah.
Not with this. I mean, yes, you could in theory. I mean, but you need for the state you need to access it in a certain way, like have a certain structure to be able to access it fast. So maybe someone come up with an idea to keep the properties of logarithmic access on the state and still be able to compress it. But this does not apply directly to the state.
Okay, thanks.
Awesome. Yep.
So you mentioned a few times that it's necessary you're gonna make the miners do the compression. So how about making them do anything? The miner, so there's no one, unless it's Vitalik. Like, how are you gonna make all the miners do something? Because even if you take the load off them, even they could be losing money in some situations, right?
Well, this protocol have economic incentive for everyone. So in the case of the BLS compression, there is a special fund that is taken from each transaction that goes to the miner to make this aggregation. So you could come up with an economic model so that the ones that compress the blockchain are incentivized. I don't know if that was the question.
So just how are they incentivized to do so? If
Okay,
we take the load off them.
Individual users are incentivized because each time a user submits a new transaction, it gets a reimbursement for the previous transaction. So it doesn't, each transaction, each user transaction does not pay for the signature size or for verifying the signature because it's saving. And the miners get also a refund when they aggregate transactions. But the cost of aggregating signatures, the cost of aggregating signatures is very, very low for miners because they are not aggregating signatures for every transaction, just for one transaction per account, which is a lot less.
Thank you very much for that. Can we have another round of applause? That's awesome. Okay.